Hello, statistics student. This video is for chapter 8.1, confidence interval for mean with one sample when sigma is known. So this topic is really long. It is very technical also. So are we talking about when we say confidence interval and mean, one sample, sigma? What is it about? So let's go over some of the terms. If we are measuring something, and we get a sample. So for example, this is the population. We can talk about the population being a lot of people, like maybe we're measuring height, for example. And then we just sample a few. This is a sample. You're measuring something, right? So this is one sample, and we have a particular sample size, maybe 10 people. This population should be very big, something like that. And so the population mean of everyone's height, mean height of everyone is mu, right? Population mean. But if I calculate the mean of this sample, that is x bar, right? We are measuring something, and that is mu. It's all about height, but if you are measuring everyone that you want to study, that is mu, called population mean. And if it is just from the sample, you calculate the mean, that is x bar. Sample standard deviation is S. So in these samples, how the different heights deviate, like varies. So that would be S. And you can use a statistical calculator to find sample mean, sample standard deviation. You can also use it to find mu and population standard deviation sigma. So SD, if it's from the sample, it's called S. SD, if it's from the population, is sigma. So it's all Greek letter if we are talking about this summary of a population. Sigma. Look like an O, but it's sigma. Mu is population mean. So both of these are population. Okay. And these two are sample. So 4 terms, you should have known them. And then sample size, so I have 10 and like 10 people in this sample, so size will be n. What is confidence level and what is significant level? So 2 more terms. I think significant level you might have heard before. Significant level was alpha. Another Greek letter. Alpha is what is unlikely, and we know by default unlikely probability is 0.05. So confidence is the opposite of significant, is what is likely to happen, what can occur by chance, not unlikely. So we say confidence. That means I can see them. I'm confident that they will happen because they could have occurred by chance. So the percentage of the uh, probability that is going to happen is sea level. And of course, they are complement of each other. So if you have alpha, that would be 1 minus sea level. If you have sea levels, it will be 1 minus alpha. Okay. So the sea level abbreviation, there is no letters. They just say sea level. So we have all these 6 terms. Now, what is the purpose of 6.1? The purpose of 6.1 is to, if I have a sample from, pick from a population, how can I use X bar to estimate what the actual mu will be? So the goal is to use X bar to estimate mean, the population mean. Of course, you cannot just say X bar is equal to mu because it would change every time. And also your sample size usually are smaller. So how can you be confident that X bar is exactly mu? Mu is just one number. But we know X bar varies, and it varies in a certain way. So according to central limit theorem, if the sample size is greater than 30, there is a special feature of X bar. Do you remember when you do the central limit theorem activity, X bar has a sampling distribution that is normal, always normal. We even know the bell curve that has mean equal to mu, which is the population standard deviation, although we don't know what it is, but we know it is the same mean, and the standard deviation is sigma over square root m. You may say, Ms. Chan, I don't even know mu, but you can kind of know the shape is around this. I only have one. One is X bar. I cannot tell where mu is. That's true. But behind the scenes, we know the central limit theorem work that if you collect a lot of X bar, they will behave this way in the bell curve that we are seeing here. Now we do not know where mean is, but we know the SD. That means we know how much each tick mark is. So this is not necessarily 2 tick mark. By default, it could be 2 tick mark, right? But we know how each tick mark works. Each tick mark is sigma over square root n. So if I know the tail, which is unlikely, these are unlikely, significant, where the middle is confidence. So if I'm confident that my X bar will show up here, because I collect one, right? So these X bars should, at minimum, it would be the low end here, right? So it's my lowest X bar, or it would be my highest X bar here because I am confident that I only get these. These are not supposed to happen. In statistics, things that are unlikely is not supposed to happen. So then you would say, well, if that is the case, the error from the actual mean would be how wide this is, right? And we know that this number can be found by finding the z-score, finding how many z-score corresponds to alpha over 2 at its tail, and multiply by sigma over square root n, because this is the standard deviation. Oh, one thing I want to say is, although we call it standard deviation, to distinguish it from sigma, sigma is this actual standard deviation from the population. This is also called a standard error. So sometimes you would see books refer this as standard error. Why? Because it can be used to calculate margin of error. The margin of error where X bar is away from the real one can be as far as the z-score of this tick mark times each of the standard deviation, which times each tick mark, which is sigma over square root n. So we have if I have an X bar, I know that this X bar would have a maximum error of z critical value z alpha over 2. Why is it alpha over 2? Because if the middle is sea level, the 2n is alpha. So each of the two tails will be alpha over half. So this z tick mark would be z alpha over 2 times sigma over square root n. And this is the maximum error my X bar will have. So that means if I want to find mu, I just have to add my X bar to this number or minus it. Then I will cover the real mu. Okay, so that means a range of value from X bar minus the margin of error to plus the margin of error. Sometimes in layman's term, we say plus and minus the margin of error should include the real mean at a confidence level of C level, because these are what I identify as confidence. So that's what we are talking about. When we have one X bar, we can't do much because we don't know if it is exactly mu. We just don't know. But we can use this X bar to construct something called a confidence interval. That's what we talk about, confidence interval, in the form of X bar plus and minus E to estimate what mu would be, possibly would be. Okay, so the formula. If I have one sample with size n, sample mean X bar, sample standard deviation S. Well, actually, I do not use S at all. Or I actually have data, and I know my sigma is given. Then I can say point estimate of mu is X bar, but we seldom use it. Okay, so if someone asks you, just give me one number of mu, then you say, well, just take X bar because that's the only thing I can get. But this is not accurate, right? It's just one number. I want an interval. I want it like a range of value that my mu may be. So what I can do is calculate the error bound, the largest error that it may be, and it would be z alpha over 2 times sigma over square root n. And then the interval would be this X bar minus the margin of error to X bar plus the margin of error. And we call it an interval estimate. It's a range of number with a lower limit and upper limit. So when we write a confidence interval, there's three formats. We can write it as an inequality, having mu in the middle, because we're actually wanting to estimate mu, the population mean. And so we will say mean is between, so this format, uh, less than with mu in the middle means mu is between the low number and the upper number. So it's an, like an algebra term. The second format is a plus and minus format. So you just say, oh, it is x bar plus and minus e. I don't know where my x bar is, but if I do a plus and minus of this margin of error calculated this way, mu should be inside. Okay, the third interval would be use the like pre-calculus and calculus format, which is have the lower limit, upper limit written in like a comma form and a bracket or a parenthesis. The parenthesis like that. So you write parenthesis lower limit, comma, upper limit. That means from kind of like the, so you can kind of read it as a number line. This is the low limit, and this is the upper limit, and all the mu would be here. So this is what the interval. So that is not all the mu. There's only one number, but mu would be in any of these, possibly in any of these. And the reason why you are sure is because mu should be different from any x bar at a maximum of e. So if you do plus and minus, it should cover it. Okay, so let's do a calculation using this formula. So remember this formula. The interval estimate is you find the margin of error and then you minus and you plus. Okay. The margin of error is found by finding the z-score with a tail of half of alpha times sigma over square root n. And because of that, you notice that sigma must be given. You must know sigma, which is the population standard deviation. So the first one is a really easy one. It says no sigma or anything. It's just say that you have a sample and someone has calculated the margin of error at 1.3. So please find the confidence interval. Well, the first is the plus and minus format, right? So you would say, oh, it's x bar is 8, so this is 8 plus and minus 1.3. That's the first one. The second is use inequality. So you can actually just look at this and then do the two calculation. You will say, okay, mu would be equal to, well, actually you should say mu equal to, well, don't write this, would be 8 minus 1.3, use a calculator. 8 minus 1.3 be 6.7, the lower limit, and then 8 plus 1.3 would be 9.3. So this is the second. The third one is use the calculator, like a lot of graphing calculator use this. Use the bracket, the parenthesis. We call it interval notation. Would be just write the first one number, the upper and the second number. So this corresponds to a number line having the left bound 6.7, the right bound 9.3 basically. If you look at this or you look at this, you can draw the number line. Example 2 will be you actually have to apply the formula. So you have a sample size 40. That means there's 40 data. And you calculate someone's calculated sample mean is 76. So x bar is 76. Population standard deviation sigma is 6.5. Find z alpha over 2, that critical value, for 90% confidence interval. So you have to do confidence interval. You want to calculate this so you can find E, right? Because if you look at the formula, it depends on this critical number. The Z is the tick mark that corresponds to a right tail of the leftover of 90%. So in a nutshell, you can say, oh, if it is a standard normal of Z, the middle, 90% is those are in the middle, right? This is 0.9. What is this cutoff, right? So that this is half of the tail. So the two tails will be 10%, so this is 5%. So you can actually say critical value Z would be having 0.9 in between or 5% above. Either way is fine. So I have an inverse inverse normal calculator. Use Z because I want to do Z, right? So I like to do middles because I don't want to do any calculation. It's 0.90, 90%, change to that. And I say in between. If I do in between, then I know that one is positive, one is negative. I want the positive one for calculating the